Well, all right then. Let's get started in on our first major topic that we're going to deal with in this class, GIS data. All of the information that we work with in this class, one way or another, comes from reality. And I've got this slide in here to remind me that um, of the basic data that we use in the workbook and in the exercises that I have for you that focus on Bonner County in Idaho are going to come from real world data sets, both of the physical environment and of human demographics, economics, things like that. The ones for the textbook are a little bit more canned and processed, and they're designed and modified to work well within that context to give you a good exposure to different forms of data. The data that I use in what I call the practicals, which are essentially quizzes and exams over the material, you'll be using real, unvarnished data sets from Bonner County, from the U.S. Census, from the U.S. Geological Survey, and other sources. But those are going to be sets that may have problems, they may have issues, they may be data sets that you need to explore and understand as you're using them in the class. But the whole idea behind geographic information systems is that they relate back to actual, either physical, natural landscape phenomenon, atmospheric phenomena, climatic data, or things that we measure about human populations. And we can take that information and we must be able to attribute it to geographic space, which is then what we analyze in our GIS programs. So, two of the types of information that we can store in geographic information systems, which I will be calling GIS from here on out, are not necessarily the actual data formats, but things that exist out in nature. So discrete objects, things like individual roads, houses, states, counties, as it's indicating on the left-hand side of this slide. There are things that kind of stand alone on the landscape, and they may be built, they might be naturally occurring, but they're things that we can represent as individual objects on the surface, as opposed to the surface itself, which is more continuous data. So, for example, elevation is one of the major ones that we use in all kinds of analysis. Every location on the Earth's surface has some elevation above or below mean sea level. And so that's something that we can measure and we can put into a particular data format. Other naturally occurring environmental variables or environmental characteristics, be temperature, precipitation, things like that. The amount of solar radiation that a location receives throughout the year would be another good example. So we can break the world down into these two categories, and then we have data formats within which we store that information. Here's an example of the kind of a map that you may or may not have used much in your life at this point in time, but the USGS puts out different series of maps. This is an example of a 1 to 24,000 scale USGS quad, a 7.5 minute quad, looking at some detail of it. And we're taking information about the Earth's surface, converting it into two-dimensional representations on what we call a map. Okay, so maps are something you're probably used to using them in one form or another. You may or may not have used paper maps very much in your life, depending upon what generation you are. You may be more used to interactive digital maps on your phone, on a tablet, on the computer, or if you're an older person like me, you may have grown up using nautical charts and topographic maps your entire life. And it's just And then now we are using digital maps in modern life. But anyway, um, what we see on these types of maps is a lot of information about the Earth's surface and a lot of information about the human built environment. And we can break those down into categories that you can see on the slide: point features, line features, polygons, annotations, which are text. So each of those groups of objects tells us something about what's going on the Earth's surface. If we know from a map legend or a map key what the individual point symbols mean, then we can interpret this map and say, well, those little squares, they're buildings, they're residences. So those are all maybe individual houses in this neighborhood. The line features may mean different things. In this case, where we're most likely looking at different forms of roads, state highways, maybe county highway, um, things like that. So each symbol has meaning within its category. There may be more than one type of point feature, more than one type of line feature. When we alter the color, shape, and texture of those objects, they convey different meanings and they represent different things on the Earth's surface. Polygon features describe area on the Earth's surface. The one that's being called out by that little bubble is industrial waste ponds. So a place where effluent goes and hangs out for a while and settles into the pond, and then the water can be scraped or siphoned off, and the waste can be scraped out if need be. Um, and annotation features then text that describes something on the Earth's surface. So here, neighborhoods: Loxley Gardens, Geneva Park, um, Broadmoor that we can see on the map. Also, physical features like the St. Julian Creek or St. Julian River, maybe. If we were looking at a larger area, we might see mountains where the text is stretched across the mountains to indicate not only where the mountains are, but that they occur stretched across space. Um, One of the things to note on these types of maps is that whenever you see the color purple, it indicates that this is a change from the last revision or version of the map until the new one. So this is these industrial waste ponds and some of those buildings that exist more towards the lower center of this particular map, and over by Geneva Park, just south of the creek, there's purple in there. That means that those are physical objects being depicted on the map that weren't there the last time the agency made the map. And that's just a little quirk, something to remember when you're dealing with government maps, and especially USGS map series. Purple indicates change that's happened between different versions. So I think, yeah, I've pretty much covered all that stuff there pretty well. So one of the advantages of using GIS and maps is that we can take the complexity of the Earth's surface and make it a little bit more abstract and something that we can conduct analysis on. So this slide is showing us two different views of the same neighborhood. On the left is a high-resolution air photo or a satellite image that we can see a lot of detail on. Individual houses, cars, boats, that pool in the backyard, and even individual trees and the branches on the trees, their shadows. So there's a lot of fine detail in that. And when we are working in GIS and remote sensing, um, quite often we'll need to take that information and make it a little bit more abstract. So we generalize. And so on the right is one of the data formats that we commonly use in GIS. It's an example of a raster format where individual picture elements or pixels, little squares, are representing areas and objects on the surface. And what's happening in here is that it's not doing a great job of depicting the reality of this particular neighborhood due to probably the nature of raster data and whoever created it just didn't do a very good job of it. But you can see the idea that we have here is that we are trying to represent reality in a form that's a little bit more portable and something that we can eventually analyze using GIS analysis techniques. Related to generalization is the concept of scale, map scale, and the scale of Earth as we experience it in our daily lives. So when you ever see or hear in the textbooks, the literature, anything that is referring to scale, it's some sort of a comparison to the actual distance on the Earth surface to the distance on the map. So we're seeing two examples of that on this slide over on the left, where there's a scale 1 to 24,000, and then below that there's a map with a scale of 1 to 50 million. So what that means is 1 inch on the Earth's surface, for example, would mean 24,000 inches on the Earth's surface on the upper map, or 1 inch to 50 million inches on the lower map. It could also mean 1 foot to 24,000 feet on the upper map, 1 foot to 50 million feet on the bottom map. Map scale itself is unitless. It doesn't have spatial units. We can use any particular spatial unit that's reasonable to measure distances on it, though. Okay, so if that's something that's new to you, you might want to reread it a little bit in the texts and see what's happening with that. But it's known as in this case, as a representative fraction, or 1 inch, or 1 unit on the map represents 24,000 units of real space, or 50 million units of real space on the map. And so scale is inherently something that we have to deal with all the time in geographic analysis. It really influences just about everything that we do, and especially in these different data formats that we have access to. It really does play a big role in how well our data can represent what's actually out there on the Earth's surface. And here's some examples, and using a couple terms that you might find in literature: large scale map, intermediate scale map, and small scale map. So this may be a little bit different from the way you're used to thinking about scale when you hear it on the news or see it in a movie or something like that. Large scale effects, small scale effects, it's kind of the reverse of what people normally think. Because in geography and cartography, the large scale map is referring to the size of the fraction, the representative fraction. So if it's larger scale, the scale is closer to 1 to 1, which means that the map is being drawn, derived, described at a level that's closer to what's at the Earth's surface. Okay, it's like flying overhead on a kite for a large scale map, and on a small scale map, you're flying overhead in the International Space Station. And the small scale map represents a larger representative fraction. So, in this example here, again, from the previous slide, the large scale map is 1 to 24,000, which is a lot closer to 1 to 1 relationships. The small scale map is 1 to 50 million, which is much further away from a 1 to 1 relationship. Okay. And the intermediate scale map is kind of a gray, vague area. It lies somewhere in between those extremes. Generally, you might think of it as between 100,000, 1 to 100,000, and maybe 1 to 500,000 would be intermediate scale. So anyway, this is, again, it's just some examples of when you're at different scales and the map is being drawn or digitized at different scales, it's going to have an effect on the accuracy of the details that you're trying to preserve in the map. So think about the one on the left. If I was to try to trace the outlines of all those polygons, to trace where the different road features are, the line features, and to identify the locations of each of those points, I can do that really well. And I can produce a fairly accurate digital representation of that. Now, if I was trying to do that same work on the map down in the lower right-hand corner, I'm not going to be able to pull it off. I don't have enough detail. I don't have enough space because it's showing me so much more of the Earth's surface. I don't have as much detail available there. So if I was working at tracing the river system in the map on the left, or even the map in the center, I'm going to do a better job of tracing where those things are than I am if I use the map on the lower right. It's just going to be more accurate when we have larger scale information to work with. Smaller scale information is going to be more prone to having error and less accurate for doing landscape level types of analyses. So we've got discrete and continuous forms of data, and now we need to put them into some sort of a digital mode that we can actually use in our GIS systems, something that we can analyze, something that we can store. And the two models that we have generally are vector and raster. Vector meaning points, lines, and polygons, and raster basically meaning squares. Sometimes rectangles, sometimes other shapes, but most often squares, where each side of a square represents the same amount of distance on the Earth's surface. And so they're kind of representing areas in raster model. Vector is a lot more accurate. Raster, not so accurate. Each of them have different capabilities and different advantages and disadvantages that we'll be exploring throughout the class. But these are the two major data forms that you're going to be using to examine, explore, and analyze phenomena about the Earth. So vector data model, shown here in a little bit more detail. Think about it kind of like a graph. So we have X and Y dimensions in 2 dimensions, and we have some origin point that's shown here on this really generalized graph. And every piece of the vector data model can be described in distances away from that origin point. Just like if you're graphing information for anything else that you might have done in the past. Except here, instead of graphing like the trend in temperature changes throughout the day or something like that, or how much precipitation we're getting throughout a month on a daily basis, what we're doing is we're graphing where locations are relative to the origin point. Okay, so where X and Y intersect is our origin, and then we can count units up and down, north or south, right and left, east and west of that origin, and then we can locate objects in space. So we can or what we can locate for the vector data model, the basic foundation of it is the point. Okay, that's the smallest thing that we can describe as individual point locations on the Earth's surface. If we connect points, then we can create a line describing maybe a river, maybe a road, railroad, a runway, linear type features on the Earth's surface that move from location to location. And then if we combine all those things, combine both those together, points and lines, and then wind up with a line that starts in one location and ends in the same location, that can enclose an area, and that's known as a polygon. And so we can use these to represent just about anything we want on the Earth's surface, and we can do it with a high degree of accuracy and precision, because points, as you might remember from high school geometry, don't really have dimensions. So they're very small things. When we're surveying locations on the Earth's surface using modern surveying equipment, we can be incredibly precise about where those things are. Or if we're using a high precision GPS, we can measure point locations very accurately and then transform those into data points in a GIS to describe locations, linear features, in areas.